Hello, welcome to the course on spectroscopic methods of analysis. In this course, to begin with, we will talk about the basic aspects of spectroscopy, and then thereafter we will take up different spectroscopic methods one by one in terms of their principle, instrumentation and applications. As regards the basic aspects, we spent about 3 sessions on that. Today, in the first session on basic aspects of spectroscopy, we will focus attention primarily onto the electromagnetic radiation in terms of its nature and characteristics. The session for today is planned as follows. That is, to begin with, we will try to define what is spectroscopy, and then thereafter we will come down to the main theme of today's session, that is electromagnetic or EM radiation. And in this context, we will talk about the 2 descriptions of electromagnetic radiation. The first one happens to be the classical or wave description of the electromagnetic radiation, and having done that, we will move on to the characteristics of electromagnetic radiation. We will spend a lot of time on this because there are different very important characteristics which we need to learn about. Thereafter, we will move on to the particle or the quantum mechanical description of the electromagnetic radiation. Then we will briefly touch upon the electromagnetic spectrum, and towards the end we will sum up what we do in today's session. Okay. Now, let us begin by defining what is spectroscopy. Spectroscopy basically refers to the study of interaction of radiation and matter. Essentially what we have is, we have radiation of different kind, we have got matter of different kind. Radiation and matter, the two interact. When the two interact, the interaction can be in terms of absorption of radiation, emission of radiation or scattering of radiation. So, all those interactive things, the outcome of that is taken care of, and that actually is used in terms of trying to decipher or to elucidate the structure of organic and inorganic species. That is one of very important applications of spectroscopy. Another domain where spectroscopy comes into play is very crucial for analytical chemist, that happens to be the quantification of analyte. Yet another domain happens to be about the interaction studies between different types of species. That means we got maybe we can have some kind of a molecule there, some kind of ions are there, ion molecule interaction, molecule interaction, variety of interaction studies can be taken up with the help of spectroscopy there. Yet another very crucial domain which is very important nowadays happens to be the medical diagnostics there. Diagnostics exploit the spectroscopy in a very wide variety of ways. Okay. So, that is briefly about the spectroscopy. Essentially, just to state it again, it refers to the interaction of radiation and matter. To understand, to get deeper into that, we need to first understand what is electromagnetic radiation there. So, we will spend time on that today, and in the next session we will talk about the nature of matter there. That will be in the next session there. Okay. Now, what is this electromagnetic radiation there? Electromagnetic radiation essentially is a form of energy, and that energy is transmitted through space at large, very enormous velocities there, and in vacuum this velocity happens to be of the order of about 3 × 10⁸ meters per second, which is a fairly large velocity there. Further, very important characteristic of EM radiation is that it does not need any medium for transmission. Though medium does affect it, but it does not need it is not essential to have a medium because it can transmit through vacuum as well. Now, if you try to look into the historical perspective on electromagnetic radiation as we have today, essentially there are 2 descriptions of EM radiation. One is a typical classical description or the wave description of electromagnetic radiation there, and second happens to be the quantum mechanical or the particle description. We recognize the EM radiation more often than not in terms of the wave description or the classical description. Okay. Now, as regards the wave description of EM radiation, essentially electromagnetic radiation can be visualized as self-propagating transfer oscillating wave of electrical and magnetic fields that travel in the planes perpendicular to each other and also to the direction of propagation. Let us understand what is it. What basically we have is, we have some kind of a electrical disturbance. That disturbance is moving in space in a given dimension there. So, I say a radiation is going from say here to here. So, how do I visualize that? How do I visualize is, there is an electrical disturbance moving say like this in a direction of direction perpendicular to the propagation direction, and also there is a magnetic component which is perpendicular to the electrical component there. So, there are two components there. One happens to be, as shown in this diagram here, is the electrical field there. That means essentially we have an oscillatory electrical field here, and perpendicular to that we have got a magnetic field. What is shown in red over here is the magnetic component of the same thing, and this happens to be the direction of propagation. So, what we see is, there are three things here, and the three things are mutually perpendicular. So, what you see that, say this is the direction of propagation, this is my electrical field vector which is moving like this, and this happens to be my magnetic field. So, the three are mutually perpendicular to each other. So, that is by EM radiation as per the wave description there. Now, this EM radiation, we can just have a look at the animation here. So, what you see is that this first part of animation shows, maybe we can take it as the electrical vector here, which is oscillating in a vertical direction over there. But we can see the vector here, that is how is it oscillating. It goes up, comes to maximum, comes down, comes to 0, becomes negative, and so on and so forth. It keeps oscillating like that. And the corresponding magnetic vector has been shown separately over here. So, you can see that this magnetic component happens to be in a direction perpendicular to that of the electrical vector there. Let us put the two together now. So, what you see is, so this is the way we can visualize the electromagnetic radiation, that is an electrical and magnetic disturbance in space, and the two fields, the electrical field and the magnetic field, are mutually perpendicular, and also they are perpendicular to the direction of propagation there. So, that is my wave description of electromagnetic radiation there, and this animation is credited from this given source over here. Okay. Let us move further and see that how do we, what are the different characteristics of EM radiation there. As regards the characteristics of electromagnetic radiation, first the very crucial one happens to be the amplitude. Amplitude basically refers to the height of the crests or depth of the troughs there. Essentially what it means is this, that is, we have a wave which is propagating like this. I am showing only one component of that, say the electrical component here. Now, in this case, this is the height of the, this is the crest here, and this happens to be the trough. So, this is the depth of trough. Either you express in terms of height here, or trough here, or trough here, or height here. So, all this refer to the amplitude, essentially the height of it in a way. If you take a different wave, now we can see that amplitude becomes different, it is larger now. For the second wave in blue I have shown here, the amplitude happens to be more. Now, this amplitude of the EM radiation, or any wave for the matter, happens to be a measure of the radiant power and intensity of the radiation. Let us take an analogy here. Look at this picture here. I am showing you two kinds of waves on the seashore. This you see is a very mild wave, whereas this happens to be a very intense one. Without getting into it, we can just often say, because since this has a large amplitude here, suppose I am standing on the seashore here, this wave will come, just hit me slightly, and that matter will land over there, nothing will happen to me. As against that, if I am on the seashore and such a large wave with such a high amplitude comes and hits me, I will be knocked off. So, essentially the amplitude of the wave happens to be a measure of its intensity or the power here. Okay. Now, coming back to our context of the electromagnetic radiation, we have to talk two very important terms here. One happens to be the radiant power, and second happens to be the intensity there. Let us try to understand what are these and how do we differentiate between the two. The radiant power basically refers to the energy of the radiation which is striking at a given area per unit time, and denoted in terms of P. That's, we will be using it very often there. And this, since it is a radiant power, it is measured in terms of watt. That is the unit for this. As against this, the intensity of radiation when we talk about, that happens to be the radiant power per unit solid angle, and it is given in terms of watt per radian. Let us understand the difference between the two. Let us look at this picture here. Now, this I am just showing you a sphere here. if I have some source of radiation which is emitting, which is at the center of the sphere, it is emitting radiation there. So, this radiation is going through all across to the surface of the sphere here. So, that is the radiant power per unit time. This is giving some kind of radiation is coming to the surface of the sphere here. But if I take certain section of this, say this part of it, now in this part, what is the intensity of radiation coming here? That is intensity. What is coming surface as a whole is the radiant power there, and the radiant power per unit solid angle over there happens to be the intensity there. Let us understand what is this solid angle here. Now, if I have, suppose I take this sphere, cut a cone through that and look at this. If I have a cone having a surface area of about 1 meter square and the radius of the sphere happens to be say 1 meter, then by definition 1 steradian is equal to the area by r square, and since area happens to be 1 meter square, so it is 1 by, and this happens to be again 1 meter square, so it will be an angle of 1 degree. That means a solid angle subtended by an area of 1 meter square at a distance of 1 meter is 1 steradian. Now, what is the radiant power per unit solid angle happens to be the intensity. So, we have to be very clear whether you are talking about radiant power or the intensity here. Okay. Now, let us move further and see that what are other characteristics of EM radiation there. Another important characteristic happens to be the wavelength. Wavelength, as the name suggests, it is length of the wave, and it has been defined as the linear distance between two consecutive wave crests or wave troughs there. Let us look at this picture here. So, this is my typical wave which is going there. If I look at this distance here, which happens to be the distance between, the linear distance between the two crests here, or I can take this distance here between two troughs. So, this is defined as wavelength. Say if I have different wave here, so now this will be the wavelength here. So, there are different ways of looking at that, and typically wavelength is represented in terms of a Greek letter called as lambda. This symbol is very familiar, I am sure that you are familiar with the symbol lambda over here. Further, this wavelength, it will have dimensions of length here, and SI unit happens to be meter. Though SI unit happens to be meter, but we commonly use terms like angstrom, nanometer or micrometer, which are the following conversions over there. And more often than not, nanometer is most oftenly used unit for the wavelength there, which happens to be 1 into 10 to the power minus 9 meter there. Okay. Let us go further and then see that this wavelength, because we mentioned initially that light does not need any medium to travel there. It can pass through the vacuum, and the velocity in the vacuum happens to be maximum there. But when that EM radiation passes through a medium, there is a decrease in the velocity there. Let us see that what happens here. Look at this picture. So, what do we have? We have a radiation which is in air right now, and from air it moves on to a medium which is a denser medium, say glass here, and then comes back to air here. Now, what you see is that in this rarer medium of air, this happens to be the wavelength, say lambda 1. When it passes through the glass, the wavelength now becomes just this much, because this is showing the distance between two troughs over there, and again when it comes back, the distance becomes larger there. So, what you find is that lambda 2, that is the wavelength in denser medium, happens to be lesser than the wavelength in the rarer medium, which happens to be, in both the cases happens to be air. So, lambda 1 will be equal to lambda 3 there. Okay. Now, let us move further and take up yet another characteristic of EM radiation, and that happens to be wave number. Now, as the name suggests again, wave number. This is defined as the number of waves per unit distance here. Let us look at this. So, I have a wave here, and what I try to show here is that this wave is starting from somewhere here and is terminating here. So, how do I define what is wave number? If I look at it here, for this wave as shown here has 1, 2, 3, about 3.5. So, there are about 3.5 wavelengths, one wave essentially is one wavelength. So, there are 3.5 waves in this distance from here to here. As against that, if I take a different wave now of a shorter wavelength, we find that for the same distance from the same initial and same final distance over there, we find that there is 1, 2, 3, 4, 5, 6, 7, 8, about 9. So, there are 9 waves there. Essentially, since the number of waves are more, so the wave number is larger number here, and we find that there is a relationship between the wavelength and wave number here. So, what is the relationship there? That there are more waves of lower wavelength in a given distance, and that translates into that the wave number and wavelength are inversely related, and that we depict as, so this is the symbol for wave number. So, it is given the frequency symbol over here, and we put a bar on that, and that is equal to 1 by lambda. And since it is given as 1 by lambda, and lambda happens to be the wavelength which has units of meter. So, the SI unit for wave number would be meter inverse. However, commonly we used the terms like centimeter inverse rather than meter inverse there. Okay. Now, let us move to the next characteristic of EM radiation, that happens to be frequency. A frequency refers to the number of wave crests or wave troughs that pass through a given point per second. Let us look at this picture here. Let us see that this wave is moving, and we have this point of reference here. Suppose I give certain amount of time, and we can visualize that say per second I can expect say maybe 3 waves are passed through this point over there. But if I take a different wave of shorter wavelength here, then I will find in the same time more number of waves will pass through that. That means, this wave shown here in red will have a higher frequency than this wave here, which is shown in blue here, and it is a larger wavelength. So, what we see from here is that is there is a relationship between the wavelength and the frequency there. Larger the wavelength, smaller the frequency, and vice versa. Now, essentially it amounts to saying that if I have got 2 waves which are moving at same speed, the one with larger wavelength, for that lesser number of waves will pass through that, and it will have a lesser frequency there. In other words, we can say the frequency and wavelength are inversely related, and that translates into the following expression over there, nu, that is symbol for frequency over there. This is equal to c by lambda, where c happens to be the velocity of light there. Now, as the unit for frequency happens to be hertz, if you see it here, this c is velocity of light, it is meters per second, and the unit for lambda, that is the wavelength, happens to be meter. So, meters cancel, we are left with second inverse. So, that is the unit for this, but it has been given a special symbol called as Hz, or the name as hertz, just to honor Hertz, the scientist for that matter. Okay. Now, essentially the frequency of a given radiation is determined by the source, and it does not depend on the medium there. Okay. Let us move further and take up an example there, because nowadays we are talking about 4G services in the mobile sector in Indian context here. So, these 4G services in India are provided at a frequency of about 2300 megahertz. So, what is the wavelength of the radiation? Let us try to solve this simple problem over there. Just an application of the formulas we just learnt here. We find that frequency nu is to be equal to c by lambda. This implies that our lambda happens to be c by nu, and c is, we know the frequency is given to be 2300 times power 6 hertz, because this is megahertz, mega is 10 power 6, hertz is second inverse, and the velocity of light we know fairly well is 3 into 10 power 8 meter per second. Just substitute the numbers there, and what you get is lambda happens to be 0.1304 meter. That means the 4G services, the wavelength of the radiation which is coming over there, that is of the order about 13 centimeters there. That is just a simple application of the formulas we just learnt. Okay. Let us move further and take up yet another characteristic of EM radiation, that happens to be the velocity. Velocity basically refers to the linear distance travelled by the wave in 1 second, that is per unit time. And we can obtain velocity by multiplying the frequency of the radiation, which is in terms of second inverse or hertz, by wavelength, which is expressed in terms of meters there. So, we have the following expression: V, the velocity of radiation, is equal to nu, the frequency, in the units of second inverse, and lambda, which is in the units of meter there. That is, velocity is frequency into wavelength. This you must remember, because we will be using that later on. And since we have got these two units over there, the combined unit will come out to be meter per second, which we are familiar with. Typically, the velocities are in distance per unit time. So, here the distance happens to be meter and time happens to be in second. So, meter per second is the unit for the velocity of radiation there. Okay. Now, we know that we just mentioned earlier too, that is the wavelength of a radiation depends on the medium, since and our velocity happens to be the product of the wavelength and the frequency. So, since wavelength depends on the medium, so velocity also will depend on the medium of the transmission there. And velocity of radiation happens to be the maximum in vacuum, and that number we are familiar with. We typically talk in terms of 3.0 in terms of 8 meter per second, but the actual number happens to be 2.99792 and so on and so forth. And velocity in vacuum is given a symbol c there. The typical difference between the velocity in a given medium and that in the vacuum is very, very small. It is less than about 0.1% there. But let us see the reason for that difference to be there. Look at this animation there. So, what do we see here? What do we see here is that when the radiation was passing through the medium, it had to interact with the constituents of the medium, that is the molecules over there, whereas in vacuum it just passes through straight. So, it moves faster in the vacuum than in the medium over there, and this animation is credited from this given source over here. Okay, let us move further and move on to the second kind of the quantum mechanical description of EM radiation. This is called as a particle description there. Now, as against the classical or the wave description, particle description is totally different over there. According to particle description, we find that the light can be described in terms of packets or particles of energy there. Now, suppose we have got a source of radiation there, when the light is passing or coming out of it, or the radiation is passing, that will be in the form of the packets of energy there. Essentially, we said earlier that EM radiation is nothing but energy which is being transmitted there. So, according to wave description, energy is transmitted in terms of a electrical and magnetic disturbance over there. As compared to that, the particle description says that energy is transmitted in terms of packets of energy, and these packets of energy are called as quanta. Quanta is the plural terms there, whereas singular is called as quantum. One packet of energy is called as one quantum of energy there. Okay. And the light quanta, because when you talk about EM radiation, we are talking in general, all kind of radiations are taken care of over there, whereas when we confine ourselves to the radiation, the light, as we say, the term is used as called as photon. So, general term is quanta or the quantum for the photons of electromagnetic radiation. In the context of light, they are called as photons there. And nowadays, typically we call as photons only. And the energy, because we said they are coming as packets of energy. So, what is the energy of a given packet there? So, the energy of a given packet or the quantum or a photon is given in terms of the following expression: E is equal to h nu, where E happens to be the energy, h is the Planck's constant, and nu happens to be the frequency there. Now, we find that this is very, very crucial expression over there, that is the energy of radiation is related to different characteristics over there of the radiation there. E happens to be h nu, we just said there, and if we just put expression for nu here, that is c by lambda, so the expression becomes E is equal to h c by lambda, or if I just take 1 by lambda to be nu bar, that is a wave number. So, E happens to be equal to h c nu bar. So, there are alternative ways of looking at the energy of a radiation. It E is equal to h nu, or E is equal to h c by lambda, or E is equal to h c nu bar, because all these expressions are very, very useful when we try to express energy of a given radiation in terms of different characteristics over there. We will take a simple problem on that, and we just mentioned that h happens to be Planck's constant, whose value is 6.626 in 10 to the minus 34 joule second, and velocity of light we are talking about many number of times there. Okay. Now, let us take that one very important conclusion we can draw from this expression is, that is the energy happens to be proportional directly to the frequency and the wave number, because E is equal to h nu and we had E is equal to h c nu bar. So, nu bar, that is a wave number, and the frequency, the energy happens to be directly proportional, whereas for the wavelength there is a inverse proportionality over there, because we have E is equal to h c by lambda. So, according to that, if the wavelength becomes lesser, the energy will be more, because this will be seen many often, because when we talk about the interaction of radiation and matter, we will see that how does the energy of radiation come into play there. We will talk about that when we talk about different spectroscopic methods there. Okay. Now, And we also know that higher the frequency, essentially we are just trying to translate this statement over there, that is there is a direct proportionality or there is a inverse proportionality there. Okay. Now, this is crucial, that is the radiant power of a beam of radiation is directly proportional to the number of photons emitted per second. That is very important, because when we visualize our radiation in terms of packets of energy. So, how many packets of energy are getting to a given kind of a target over there. So, that is the radiant power over there, because we define radiant power in context of wave description was that radiations are coming there, how much of the power is coming to the surface of the sphere, we just saw in that animation over there. But now we are talking in terms of how many photons are striking or reaching out a given target over there. So, the two ways are slightly different over there. Okay. Let us move further and take up a simple example again, just an application of the formulas we just mentioned here, that is what would be the energy of a photon of a microwave radiation having a frequency of 2300 megahertz used for 4G services in India. We just took the same thing, but in different context there. Now, I am talking about the same radiation there, because we remember that 13 centimeter was the wavelength of the radiation. Now, we want to find out if that the microwave radiations which are used for our 4G services, what is the energy of that kind of a photon. Let us look at that. We know that energy of photon is given by E is equal to h nu, and h we know is the Planck's constant having the following value there. Frequency is given to us as 2300 megahertz, 1 mega stands for 6 and hertz is per second there. We put it over there, substitute the values and we get E to be equal to 15.24 in 10⁻⁻25 joules. So, that is very tiny amount of energy which is there for a given photon of the radiation we are referring to here. Okay. So, having talked about the classical or the wave description of radiation and the particle description, let us move on to another very important domain which is of relevant to us, is that is called as a electromagnetic spectrum. This picture I am sure that you are familiar with, you must have come across this picture very often there. Now, as the name suggests, it is electromagnetic spectrum. This essentially is a spectrum of all kind of EM radiations there. This actually shows that we have got a whole spread of all kind of electromagnetic radiations, and they extend from about gamma rays to radio waves. Radio waves are of very large wavelength over there. Gamma rays are of very short wavelength, and we know that how do the energies come over there, because there is an inverse relationship between the energy and the wavelength over there. Further, one more thing we can note from here is that is this typical rainbow kind of a thing, VIBGYOR, the visible spectrum, that happens to be a very tiny part here, because out of the whole spectrum starting from gamma rays to X-rays to UV to visible to IR, microwave and so on and so forth, these are long radio waves over there. This is other terminal of that. Now, if you look at out of the whole spectrum, this visible part happens to be a very small fraction there. Just to make a point over there. And second thing we can see from here is that is the frequency and wavelength are inversely related over there. We see that the frequency is increasing like this, wavelength is increasing like this. That also is depicted over here. Okay, we will talk more about it when we talk about the spectroscopies of different kind. Okay. Now, let us sum up what we have done today. What we have done today is we basically started by defining spectroscopy as the study of interaction of radiation and matter, and then thereafter we took up the first part of it, that is the nature of radiation there, and in this context we defined electromagnetic radiation in terms of classical description or the wave description of that, and thereafter we discussed its characteristics over there. Then we came down to the quantum mechanical or the particle model of EM radiation, and towards the end we briefly touched upon the electromagnetic spectrum there. Now, in the next session we will talk about the nature of matter, that is atoms and molecules, what kind of quantization is there in that, and then we will briefly also take up something about the interaction of radiation and matter. Thank you.